So today we'll be talking with, the speaker is Parin Shah, who's an ML engineer and data scientist at NuData Security, Mastercard. He works on developing ML components for NuData's online security software, which protects consumers and institutions from security threats in real time. In the past, Parin has developed systems and models for fraud detection, device fingerprinting, and passive biometrics-based user identification used by leading e-commerce companies, banks, and airlines. And Parin is an inventor on more than 10 patents covering fraud prevention technologies using machine learning. Please take it away, Parin.
Awesome. Share my screen. Perfect. So I'll get started then. Hi, everyone. Thanks for joining my talk. My name is Parin Shah. I'm a data scientist at NuData Security. And today I'll be speaking about how we designed a real-time model to prevent fake signups. So let me start by telling you a bit about our company. So NuData Security is actually a Vancouver startup. We were acquired by Mastercard in 2017. As internet-savvy users, we are all generally aware of cybercrime and data breaches. Just in the last 7 years, over 15 billion accounts have been compromised, and it only takes a handful of minutes for the stolen credentials to be made available for sale on the dark web. So we all know that cybercrime is a very pressing problem. So what NuData Security does is we develop real-time products using our unique passive biometrics technology that make online interactions safer and frictionless for users. With passive biometrics, what we do is we try to observe users' behavior and use that to infer the user's identity rather than explicitly capturing a fingerprint or facial recognition to get the identity as you would in like an active biometric scenario. And the solution, the main product that we make, that's NuDetect, it's used by major banks and online stores across the world. Machine learning is used in a lot of products that we develop. Certainly, we have the product around preventing fake signups, which we also refer to as the online account origination fraud detection product. So I'll be going into detail about this. But we also use it to power several of our other solutions. I won't go into details for these ones, but I'll leave these here for when you get to look at the slides later. Okay, so let me introduce a problem statement now. What are these fake signups? So we know that stores and banks offer credit cards, reward cards, and these end up being prime suspect for fraud as there's money involved. What fraudsters do is they use stolen identities or synthetic identities and automation to sign up for these cards. Eventually, this leads to unpaid balances. It leads to chargebacks. Chargebacks is a scenario where the true customer would then call up their credit card issuer asking for a refund. And in general, this all really leads to big losses for the institutions and the merchants involved. So what we did is we built a product around this. We use supervised machine learning to predict these fraudulent signups, and we offer this to our clients as a real-time, low-latency inference service. And the real-timeness of this model helps us stop high-volume attacks quickly. So if you contrast this with like a batch inference, that's you're generating your predictions every 6 hours, fraudsters could incur significant damage. So being real-time really helps us prevent the attacks before they become larger. So as machine learning practitioners, we all know that feature engineering is one of the most important aspects of a model. If you don't have good data, garbage in, garbage out. So we use features to inject domain knowledge, and this domain knowledge then helps us detect these fraudulent and non-human-like form-filling patterns. The raw data that we use to generate these features on is generated by our passive biometrics technology. So the data that we use is data about keystroke dynamics, so a user's typing speed, how much time does a user spend between different keys on average, what is the velocity of your mouse movement, how much time do you spend between different form fields, how do you hold your phone, and all of these features help us extract latent representation of bot-like behavior and human-like behavior, and then we can use that to separate legitimate and sort of fake signups for classification purposes. Let me dive into some of our tooling choices that we have developed to kind of tackle this problem. Foremost, we have developed a Python library in-house that allows all our data scientists to orchestrate different model training, tuning, and evaluation tasks. The library is designed to provide experimentation consistency and reproducibility between different projects and teams. And under the hood, we use Luigi, which was initially developed by Spotify to orchestrate all the tasks. Luigi is a batch pipeline management and orchestration tool, so it's kind of similar to Airflow in various respects. On the right, you actually see a screenshot of the scheduler interface that Luigi provides. And Luigi also uses the notion of DAGs, or the directed acyclic graphs, to help you represent a task and manage all your task dependencies. So this library that we have designed supports common machine learning frameworks like scikit-learn, XGBoost, and HyperOpt for hyperparameter tuning. And we use AWS S3 as our metadata store for tracking all experiments and versioning all experiments. And this is very useful as multiple data scientists are often experimenting simultaneously, and we get automatic documentation of our results as well. So this whole library is used by simply providing a YAML configuration files. So data scientists can actually train models without really writing much code. They write this YAML configuration files where they define what kind of a task they want to run. So model evaluation versus hyperparameter tuning or deployment. Specify what pre-processing steps that need to be applied, what kind of an estimator needs to be applied. And through this configuration file, data scientists can also include these proprietary pre-processing and custom models that we've developed. And this is then used to train the model. And then once we have a trained model available to deploy it, we have gone to develop a specific, like domain-specific language for model deployment. And this is used by different user groups in our company. So what are benefits of this DSL? So DSL is designed to be non-developer friendly. So user doesn't need to code, doesn't need to push anything to Git, or you don't need to have any development environment set up to be able to deploy your models. We have an internal user interface that's available to all our staff, and the DSL can be inserted there. And this DSL itself is version controlled, so the models are version controlled, and this also allows for easy model rollbacks. DSL also helps us decouple offline model training and deployment. So data scientists can train models independently, version independently, and then production deployed models can be versioned separately as well. And one of the most important benefits is that it allows our customer success teams to act quickly to customer requests. So if we end up in a scenario where a model isn't, there's a novel attack and the model isn't performing well, the customer success teams can either quickly roll back the model or change the classification threshold used for the model. But just being able to act quickly really helps with this DSL. Here's a snippet of a sample code that's written by a data scientist to deploy a model. It's just a JSON snippet. And here's another snippet that shows how an integration engineer or a customer success team member would actually use the inference provided by the model. So here in the snippet, you see that whenever the classification threshold of 0.5 is breached, we serve an introduction. So introduction simply represents what we're going to do with this score. And in this case, we would serve a CAPTCHA to the user to further verify their identity before they can continue on their flow. But then an integration engineer is able to choose from various different introductions by working with the customer. So following these processes and these tools, we have deployed such models to serve hundreds of transactions per second with a really low latency. And you kind of follow all these textbook knowledge on model development, and yet you notice that the performance deviates from what you theoretically expected during your cross-validation exercise. And through monitoring and research, we were able to find some of these common pitfalls. So I want to share them, just want to share some of them at least to make others' journey easier. One of the first lessons refers to concept drift and feature drift. So concept drift is a phenomena in machine learning that refers to the changes in relationships between input and output data over time. And whenever concept drift take place, the model's performance also degrades. So this is very applicable in our scenario, as fraudsters and their strategies that they use are constantly evolving. So the same feature values and distributions that could once identify fraud no longer can. On top of that, let's say you saw that credit card application form earlier. We have features built on top of that. So when the design of the form changes, as the client changes their form design, the features built off of that, the distribution also changes. So time spent on page would be conditional on the form design, and hence if the form design changes, the time spent on page will also change. So this is how concept drift and feature drift arises. So how do you go about resolving this? One simple answer to this is model retraining, but then it's difficult to determine when to retrain. So if you did have access to automated frequent labels, then you can always keep monitoring your model performance. And whenever the performance drops beyond a specific threshold, you can trigger your retraining. But as we all know, generally label collection is really expensive. And in certain scenarios, labels are not available until a significant time has elapsed. So the alternative here is we can measure the changes in data or feature distributions over time. And there are various different statistical metrics that we can use to compare distances between two feature probability distributions, such as scale divergence or the symmetric version, which is the Jensen-Shannon divergence. And here's a screenshot of a sample feature drift detection dashboard that we have built. This dashboard shows you two distributions. One is the distribution of the training features and the distribution of serving features. So whenever the serving feature distribution starts to differ significantly from the training feature distribution, our model would then send out an alert saying the drift value has been exceeded. And then this is what we use to trigger the retraining of our model. And this is one of the important principles behind machine learning, that the distribution of your features that you experience during during training is what the model should be serving on as well. And if that principle doesn't hold true, that's when the model's performance degrades. One of the other silent killers of model performance is feature calculation inconsistency. So it's common that data scientists are responsible for model training. So data scientists use data from a data warehouse, the typical analytical data source, and then data scientists write the logic for training feature calculation using the tools that data scientists are typically familiar with, like pandas and Python and Spark. And then they use this feature calculation pipeline to generate their training data set. And eventually, when they're ready to deploy a model, that's when developers engage. And here, the data source ends up often being different. It could be a transactional database, or it could be like a Kafka stream. And then developers then implement their own logic for calculating features for serving. And this could be done in a different language. And data scientists are, in fact, often not even privy to how this is exactly implemented. So to them, this is kind of like a black box. So now we have different sources for training and serving. We have different languages that are potentially being used. So we have different algorithms and different approximation. And what that means is that a feature is calculated in a certain manner during training, and it's calculated in a different manner during serving. And this leads to this feature calculation inconsistency. And again, we are in a scenario where the training feature distribution doesn't match what your model is scoring on. And this degrades your model performance. One of the other side effects of this is that it's difficult for data scientists to implement new features in production. Data scientists can quickly write their NumPy code to implement training features, but getting it to work in serving would require pulling together various extra resources. So how do we go about fixing this problem? So to address this, we have purposely built a feature store, which is literally a store of features using various managed services on AWS. Let me explain what feature store does in a bit more detail first. So feature store provides a common interface for extracting features to prepare your training data set and to extract features for model serving. So you no longer have a separate pipeline for training and serving. You use the exact same data source, and it's the exact same feature calculation logic, just implemented once. And it helps you prepare your training data set, which allows feature time travel and gives you this point-in-time feature value correctness so you can know exactly what was the value of a feature for a given historical event. This is pretty important as labels are generally only available for historical events. So you can know, okay, I want to know what is the value of this feature for this user jane@doe.com 7 days ago. I can fetch that through this feature store. And for model serving, it gives you access to low latency feature lookups. So you can use that for batch inference, but more specifically for real-time model serving. Some of the other benefits includes that one, it helps empower data scientists, as data scientists can write the feature calculation code, and that's used both to prepare the training data sets and used for model serving. It enables feature discoverability across teams. You can share features across model, so it also becomes more cost effective as more and more features are being shared across models. There are a few open source and closed source feature stores out there. I'm going to leave some links here if you want to read a bit more about feature stores. Okay, so now that you know what a feature store is, let me tell you how we have architected it on AWS. So we have two data sources that we primarily use. One is our S3 data lake that contains our longer term historical data. Then we have an Amazon Kinesis stream, which contains our near term data. And by near term, I mean data from the last 24 or 48 hours. So the stream basically contains a subset of the data that the data lake contains. All right, but it's still the same schema. And I'll tell you why we have these two sources. So first of all, this whole workflow of feature store is triggered by data scientists adding feature logic. So data scientists would push some code to our feature store registry, which in our scenario includes PySpark code, and it contains feature definition and the feature implementation. It's just a PySpark script plus a YAML configuration file. And then once that code is pushed, it deploys certain resources on AWS, so cron schedules, CloudWatch rules, and it deploys its feature generation jobs. And then this kicks off the step function, which in turn launches these feature generation jobs. So there are two kinds of feature generation jobs here. We use AWS Glue to run them. So Glue is a managed Spark service on AWS. So we use the standard Spark to run our batch jobs and Spark streaming to run our streaming jobs. So the AWS S3 data source is used to run the batch job. So let's say if you have a feature that operates on slow moving data. I'll give you an example. Number of clicks made by the user in the last 7 days. So the value of this feature doesn't change very often because it uses 7-day historical data. So it's sufficient in most scenarios to be able to update this feature on a daily basis. So you can run a standard Spark batch job to update this feature on a daily basis. But for fraud detection, what's often very useful is having these features that are operating on fast-moving data. So let's say you have a feature that calculates the number of clicks made by the user in the last 5 minutes. Here, the value of this feature changes very quickly. So a batch job of 1 day would no longer be sufficient. So this is where we use the Spark streaming API, and we use the Kinesis stream to feed us the input data for feature generation. And then once these features is generated, we store them back in S3 in the Parquet format. We timestamp them and we version the features. And we also store the features in DynamoDB, which acts our document database, a key value store that acts as our serving store for real-time feature serving. And then the step function also pushes some feature metadata out to our Redshift data warehouse for feature discovery purposes. And then finally, we have an abstraction layer here, which is what's used by engineers and data scientists, which is a feature store SDK, which is then used to extract your training data set and get features for model serving as well. So let me show you some code samples to dive into it a bit better. So here's an example of a code snippet that shows you how I would use the feature store SDK to prepare a training data set. So data scientists would import the feature store library. They would import scikit-learn and pandas. then the user would load in some of the labels that they've received from the clients. They would load in the feature itself by making a call to the feature store SDK. So here, I'm specifying the name of the feature that I want to extract, which is my cool feature. I pass in the data frame. I pass in this key, which represents the entity against which the feature is stored. So let's say user ID, and a time column that specifies the event time for which you need the features. And then you use the feature to prepare a training data set and then go on to train your model. And in the parallel, this is how features would be extracted for model serving purposes. So again, import the features library, you load your trained model, and within your prediction event handler, you extract the entities that the feature is again store against, and then you make a call to the feature store SDK, a call to the get serving feature method here to extract that feature. And then you use the trained model to calculate your prediction and then return the prediction back to the client. So this is how we combine passive biometrics and machine learning to prevent fraud and fake signups and prevent losses for our clients and merchants. As takeaways, we have developed a Python library on top of Luigi for consistent and reproducible model experimentation. We use a domain-specific language to really enforce this idea of low-code model deployment to be able to mitigate model drift, which is one of the frequent consequences of deploying model, is we monitor changes in feature distributions and use that to decide when we want to trigger model retraining. And finally, to prevent these feature calculation inconsistency, we've designed a feature store where you define the logic once to use feature to calculate features, both for preparing a training data set and to prepare features for model serving. With that, if you're interested in learning more about Mastercard and NuData Security, I'm leaving some links here. Thank you all for joining.